gravitational wave background. Now, let's start off by having a look at, if you like, the spectrum of gravitational waves. As you're probably aware by now, we have detected over 100 gravitational wave events since 2015 using the LIGO detectors in the United States and the Virgo detector in Italy. Now, here we have a scale showing you the frequency of the gravitational waves, what type of objects we can detect at those frequencies, and how we can detect them. So the first thing to say is that between the 1 and 100 hertz frequency, this is what we've been observing out at the moment, and this has enabled us to detect merging black holes, colliding neutron stars, collisions between neutron stars and black holes. And this is the limitation, if you can call it that, of the LIGO and Virgo detectors. They're observing in those sort of frequencies. So these are really quite high frequency observations. The instruments are tuned to detect gravitational waves at those frequencies. So these are high frequency, short wavelength, if you like, events. But there are other types of gravitational waves in the universe which are much lower frequency with a much longer wavelength. And in particular, we're talking about the merging of supermassive black holes at the hearts of galaxies. And this is right down here at 10 to the minus 8, 10 to the minus, well, between 10 to the minus 7 and 10 to the minus 9 hertz in frequency. These are much longer wavelength events. It's reckoned that some of these wavelengths could be light years long. And to detect these, one way of doing it is to use pulsars to detect these gravitational waves. Now, to do this, you use the thing is called the pulsar timing arrays. And astronomers have used millisecond pulsars for this. Now, what are these? These are pulsars that have got a rotation speed of less than 10 milliseconds. And we know their rotation speed incredibly accurately. They are the universe's most accurate clocks. They in terms of timing, they rival the most accurate atomic clocks that we have. The fastest spinning millisecond pulsar yet discovered rotates at an amazing 716 times per second. And they thought to spin at that speed because they've been accumulating material from a companion star, which has the effect of speeding up their rotation. But the important thing is here, they are incredibly accurate clocks. Now, astronomers have used 68 of these, all at different distances from the Earth. And as the pulsars spin, these lighthouse-like beams of electromagnetic radiation, be they X-rays or radio, flash in the direction of the Earth so that we can see them. Of course, this is greatly slowed down because these are millisecond pulsars. They're rotating once in less than 10 milliseconds. But I didn't manage to find an animation that would show you that rotation speed, funnily enough. So these are 68 pulsars at different distances from the Earth. And we know exactly, to an incredible accuracy, many, many, many decimal places, exactly how long they take to spin once. So what happens is that you have a gravitational wave which passes through the universe. And this has the effect of delaying or advancing the time at which the pulsars, the signals from these pulsars actually arrive. And by working out exactly how long these signals are advanced or delayed, you can learn something about the gravitational wave that has passed through the universe that has actually done that. Now, look at it another way. Here we have a graphic showing the Earth surrounded by these millisecond pulsars. Far off in the universe, as we know, there are galactic collisions between galaxies, where the two black holes, one in each galaxy, or in some cases more than two galaxies collide, in which case it'd be three, they come together and slowly begin to orbit each other at the center of the galactic merger. Now, they probably orbit each other for, many, many, many thousands of years, but they inexorably come closer together. And as they do, because they're accelerating around each other, they radiate gravitational waves, because anything that accelerates in the universe generates these gravitational waves. How do we know that this happens at the center of galactic clusters with these supermassive black holes? Well, we can actually see it. Here you have an X-ray image of the center of a galactic merger 400 million light years away, and you can see clearly here that there are two superheated disks of material showing up in X-rays, and if they weren't that hot, we wouldn't be able to see them in X-rays. And these two disks surround supermassive black holes. Now, to see the gap between those supermassive black holes at a distance of 400 million light years means that, of course, they're very far apart. Otherwise, we wouldn't stand a chance of being able to split those into two separate objects. Those two black holes are separated by 5,000 light years, believe it or not. That's the gap between the two you can see there. If we add the radio data into that graphic, we can see the jets of material that the black holes are firing out across the universe. And they are swept back, if you like, in this combined radio and X-ray image, because the black holes are plowing through the interstellar medium at about 1,200 kilometers a second. And this forces their jets to be swept back as if they were in a wind, if you like. So we know that we can see these black holes which one day will merge. And as they do get closer together, the gravitational waves from them get stronger and stronger. But the point is that they are very long wavelength, low frequency gravitational waves. Now, why would a pulsar either advance or retard the signal from a pulsar? So if you can imagine, you have a photon leaving a pulsar on its way towards the Earth. And because gravitational waves stretch and squeeze space-time, they stretch it in one direction, squeeze it in another, the photon will actually have to pass through a greater or longer distance, because space is either being stretched or squeezed. And this means that it will if it's being stretched, the photon will take longer to pass through the gravitational wave, because space is literally being stretched. So the photon takes a longer time to arrive at the Earth. So its arrival is delayed compared to when it should be arriving, because we know exactly when it should be arriving, because they are the universe's most accurate clocks. Similarly, if space is being squeezed, they arrive in advance of when they should arrive. Now, what astronomers have found is this, that there is a background noise in the universe of these gravitational waves, because gravitational waves, according to Einstein, and we have to say we think there are quantum reasons why this probably doesn't happen, but according to Einstein, gravitational waves never die out altogether. They just keep traveling forever. They get weaker, but they never die out altogether. So in the history of the universe, all of these mergers, and there've been probably countless mergers between supermassive black holes, all of these gravitational waves come together over time to form this background hum, if you like, of gravitational waves to the universe. And this is what they've now detected with the pulsar timing array. Now, it has to be said, first of all, that merging supermassive black holes is not the only explanation for this background hum in the universe. There are actually some quite exotic explanations that could be true, but obviously there will be more studies needed to determine exactly what the cause of this hum is. But the most likely candidate is these supermassive black holes. The project to do this, the pulsar timing array, has been running for 15 years. So they've had a chance to collect these long wavelength gravitational waves over 15 years, coming from all over the universe. And the whole point about it is, and the great thing about this is, that the pulsar timing array, well, it's one not just one group of scientists. There have been similar experiments going on using pulsars, but using different pulsars in India and other places. And there are several groups that have now all come up with exactly the same results, that there is this background gravitational wave hum, if you like, to the universe, which means that the Earth is being bathed in these gravitational waves all the time. And everything on the Earth, including you, of course, including everything on the Earth, as well as the Earth itself, is being stretched and squeezed all the time by these gravitational waves. Now, you won't feel it, of course, because the difference in size of being stretched and squeezed is about 1,000th the diameter of a proton. But it is happening, and we now have the instrumentation to detect it. So over time, all of these gravitational waves coming from all over the sky merge into this background that is now being detected by the pulsar timing array. For the future, this is fantastic, because what they hope to be able to do is to actually pin down where these gravitational waves come from, what types of objects are producing them. But as I said, it's more likely than not to be merging supermassive black holes. The International Pulsar Timing Array, these are the locations of the telescopes. We have, it includes the biggest radio telescope in the world, the FAST telescope in China. We've got the famous Lovell telescope at Jodrell Bank, of course, in the UK. We've got the Chime telescope in Canada. Arecibo, before its unfortunate demise, was taking part. We've got Meerkat in South Africa, which is a precursor telescope to the world's biggest radio telescope, the Square Kilometre Array, which will be complete hopefully before the end of the decade, although it might be a little bit delayed because of COVID. We've got the famous Parkes Radio Telescope in Australia, and we've got a couple of others. But, you know, there have been several groups of scientists working on this and asking the same questions, and they've all got exactly the same results. In fact, the different teams coordinated about when this was going to be released last week, so that nobody was scooped. And there's just some of the telescopes involved. The Jodrell Bank, of course, at bottom right, the Chime telescope above it, and so on and so forth. So that was the announcement. We finally detected this gravitational wave background in the universe, and the future for gravitational wave astronomy, which is, let's not forget, only 8 years old as a science. It's already detected this, and this science of gravitational wave astronomy, the first time we've been able to observe the universe in anything other than light electromagnetic radiation, has advanced amazingly in 8 years. And the two LIGO detectors, or the three LIGO detectors, I should say, the two LIGOs in America and the Virgo detector in Europe are now back online, working together. They came online the last week of May, and they have made lots of detections already. I was looking the other day, one day in particular, they made 9 detections of gravitational wave results yet to be analyzed. But, you know, even if half of them are terrestrial in origin, something vibrating on the Earth rather than the vibrations coming from space, then, you know, the upgrades that they've undergone over the last couple of years will be well worth it. So we're all really excited about the future of this.